We're going to look at conservation of energy. Which is nothing but the first law of thermodynamics, right? Okay. So the conservation of energy states that it is also a rate equation like the conservation of mass and the conservation of momentum, and it says that the rate of increase of energy, right, for a fluid particle, we just say Fp here, equals the net rate of heat added to the fluid particle plus the net rate of work done on the fluid particle. Okay. Just like before, we can write the rate of increase of energy on a unit volume basis, right. So then this gives us rho times dE by dt, where E is the energy of the fluid particle, right, that is the stored energy of the fluid particle, and dE dt is the rate, and multiplying by density we have the rate of increase of energy on a volume basis. Okay. And coming to the two components we have here, the net rate of heat added we represent with Q dot, and the net rate of work done we can write it as W dot. Okay. So we will first look at the net rate of work done on the fluid particle by the several forces that are acting on it, and thereafter we look at the net rate of heat added to the fluid particle. Okay. So coming to the net rate of work done on the fluid particle, we see that we have already known that the surface forces that act on it do the work on the fluid particle, right, and also the body forces as well. So first look at the work done by the surface and body forces that contribute to the work on the fluid particle. Okay. So essentially I am not going to redraw the picture that we have drawn in the last class. We have noted that for a fluid particle or for a fluid element, we have several forces acting on it, right. If I consider the x direction, the forces acting in the x direction, so what we can say is the rate of work done is nothing but the force acting on the fluid particle multiplied by the velocity in the direction of the force, right. That is the work done by a particular force, right. So that is we agree upon. So essentially force multiplied by the velocity in the same direction would give us the net rate of work done contributed by the forces in particular direction. Okay. So essentially we don't want to redraw it, but rather we want to consider the forces that are acting in the x direction first. Okay. So if we consider the x direction, if you recall the fluid element from the last lecture, we had 6 faces: east, west, north, south, and front and back. If I consider the west face, what are the forces that were acting on it only in the x direction? We had a pressure force and we had a normal stress, right, that is tau xx. Now if I use arrows to indicate the direction, on the west face we had a pressure that is acting on it in the positive x direction, right, by an amount that is P minus partial P partial x times delta x by 2, right. We are getting this delta x by 2 because the P is defined at xyz, and the west face is located at x minus delta x by 2, right, comma yz, right. Okay. And then so this is the pressure that is acting on the west face. When we multiply this by the area, right, that was delta y delta z, that was the force that is acting on the west face, right, corresponding to pressure. And then we had another force that is acting on the west face, that was the tau xx, right, and it was acting in the negative x direction, right, if I consider x to be positive in this direction, and this was tau xx minus partial x tau xx times delta x by 2. Multiplying this with delta y delta z would give me the force acting in the x direction on the west face, right. Now we are interested in, of course, calculating the rate of work done. So, we have to calculate the force multiplied by the velocity in the particular direction. So, I have to essentially multiply these two forces with u, right, that will give me the rate of work done for this. So, what I would do is I would just like before I am going to construct for the west phase, I am going to say that the work done, rate of work done for the west phase on the west phase by the pressure force would be P times U, okay, that is the rate of work done at the centroid of this fluid element, and then we want to calculate the rate of work done on the west phase. So, it will be Pu minus partial x times P times U delta x by 2 times delta y delta z, right. That would be the rate of work done. Now, of course, you can do this in couple of ways. One is to proceed the way we have done, essentially multiply P times U, calculate the rate of work done at the centroid, and then use Taylor series expansion and calculate the phase, or you could even start off with U and P separately at the centroid, right, and then reconstruct them on the phases and then multiply them together, right, in which case you would have this P minus partial x times delta x by 2 delta y delta z times you would have U minus, right, partial x U delta x by 2 as well, right. We had this before. So, you could even multiply this and get the same answer as we get here, okay. So, that would be the same that you can verify. Alright, so this is related to the pressure. Now, if we go back to the tau xx, what will be the rate of work done by tau xx? We just have to again multiply that with the direction of, right, the velocity in that particular direction, that will be tau xx times u minus partial x tau xx times u delta x by 2 times delta y delta z, right. So, this is the net rate of work done by P and tau xx, okay. Question still here, this part, okay. Alright, so then I am not going to write the forces again. So, what we will do is we will try to kind of look up directly from your notebook and write the net rate of work done on the other phases, okay. So, we have now constructed this for the west phase. If I do it for the east phase, what would be the net rate of work done? This will be P times U plus partial x P times U delta x by 2 times delta y delta z, right. This was acting in which direction? In the negative x direction, right. So, this was acting in the negative direction, so the work done would be with a minus, right, because this was minus, okay. And then what will be the other force? Tau xx, right. So, that would be tau xx times u plus partial x tau xx u times delta x by 2 times delta y delta z, and this would be a plus or a minus? This will be a plus because it is acting in the positive x direction, so it will be plus, okay. So, these are the on the east phase, right, and then we have two more forces, one on the north phase and one on the south phase, right. Similarly, we had two more forces, one on the front and one on the back as well, okay. So, essentially that would be if we write those together, that would give us on the north phase, what was the force we had? Tau y x, right, that is essentially acting on the positive north phase in the direction of x, times which velocity should I multiply this with? I should multiply this with v because, right, because why? But we are still looking at the forces in the x direction, right. So, I should still multiply this with u, right. We are looking at forces, this is acting in which direction? In the x direction. This will only do a work if you multiply this with u, right. So, I multiply this with u and plus partial x tau y x u times delta x by, this should be delta y by 2, right. We are constructing on the north phase and then multiply this with delta x delta z to get the net rate of work done, okay. Similarly, are there any other forces acting on the north phase in the x direction? No, right. So, in the south direction we have the reconstruction of this guy with a minus, right. So, that would be tau y x times u minus partial x tau y x times u times delta y by 2 times delta x delta z, right. Which direction is the second one acting? On the south. in the negative x direction, right. So, this would come with a minus, okay. This will come with a minus because it is acting in this direction, and then we still multiply with the velocity, okay. So, we have north and south. Then what about the front face? Front face we have tau zx, right. I multiply this with u only, right, because this is still the force acting in the x direction, and then because it is front face, it would be a plus partial z. I think I made a mistake here. These two should be partial y, right, isn't it? Yeah, question. With what? North and south I multiply with u, right? We will, right? I have multiplied with u. Which side? Here, yeah. So, I have taken the force here. So, the question is, do we multiply with u or not? So, this arrow indicates the force. I am multiplying it with u, right? That is what I mean. I do not mean that you multiply this again with u, right? So, this is already multiplied with u, right? Pressure times the area itself is your force. I multiply that with velocity, right? Does it clear your question? So, do not worry about this part here, okay. So, what is tau yx times delta x delta z? That is the force, right? I multiply that with u, right? Only to get an impression about whether it is positive or negative, I am drawing these arrows here, right? Okay. So, this is already, so this effect is basically what we have on the left hand side, right? Okay. Now, what about the front face? It will be tau zx times u plus partial z tau zx times u delta z by 2 multiplied with delta x delta y, right. This is acting in the positive direction, we multiplied with u. When it comes to the back face, we have tau zx times u minus partial z tau zx times u delta z by 2 times delta x delta y, right. This will come with a negative, right, because this was force acting in the negative x direction, we multiply with u, okay. Now, what is all these terms that what we have written? We have written down all the forces, right, or all the net, essentially the net rate of work done because of all the forces that act in the x direction, okay. Now, all these should be summed up, right, to get the net rate of work done by all the forces together, okay. So, that is what we are going to do. So, I am going to sum up all these things, which will give us the W dot in the x direction of the forces, okay. Now, if I want to sum it up, I want to kind of ask you to look at it before I sum it up, okay. So, what are the terms that will remain in this thing if I sum all these things? So, start with the west face, yeah. This one, because if you take the face here, right. So, this was the west face, we had pressure acting in this direction and then the tau acting in this direction. So, the pressure, so which is negative here? This one is negative here, right, is that correct? Okay. What about the east face? East face is correct, negative acting in the negative x, tau x acting in the positive, okay. So, this is a mistake, okay, thank you. What about the north and south, are they correct? Okay. Front and bottom, front and back, fine, okay. Then what terms will remain and what will go away if I club these things? What about Pu and minus Pu, right? When I club all these things, they will cancel, okay. What about tau xx times u and minus tau xx times u? So, essentially these goes away, right, this and this goes away and this and this goes away, right. So, essentially the first terms of the Taylor series expansion, right, will all get cancelled, isn't it? So, essentially if you look at here, this goes away with this and then similarly this term goes away with this term, right. Okay. So, what we end up is essentially we end up with only the second terms, and the second terms are what? Are partial x, right, with a minus here, and there is a plus times minus here. So, this is also a minus, right. So, we have one, so these are two halves sum up to 1, right. So that will give me minus, that will give me, so essentially if I look at W dot, because of the forces in the x direction, right, that will give me minus partial x p times u, right, because of the summation of this guy and this guy, right, okay, times we have delta x delta by delta z, that I have not written down, okay, I will write it down later. What else we have? We have these two terms, right, that is essentially tau xxu and here, right. So this is a plus, right, we have two minus here and then there is a plus here, okay. So we have these two terms also summing up to 1 with a positive sign. So this will be how much? This will be plus partial x tau x times u multiplied with delta x delta by delta z, which I have not written down. Similarly, we have plus, right, partial y tau yx times u, okay, fine. So this will be plus partial y tau yx times u multiplied with delta x delta by delta z, and then we have plus partial z tau z x times u. All of these guys are multiplied with the elemental volume, okay, fine. So we have now written down the rate of work done expression, okay. Now instead of going through this again for each of the phases, can we guess the rate of work done by the forces in the y and z directions? We can easily guess, right. So that would be, what would be the, then what will be the total rate? Okay, let me write down the rate of work done in the y direction, then we will write down the total rate, okay. So this will be how much? By analogy, by looking at the first this equation, right, we can write down here, this would be, this would come out to be minus partial y p times v, okay, plus partial x, this would be tau xy, right, this would be xy multiplied with v, right, okay, multiplied with v plus partial y tau double y times v, okay, plus partial z tau zy times v, right. Essentially the second index should be the same for all these, right, they are all should be y because it is the forces acting in the y direction, okay. All these guys are multiplied with what? Delta x delta y delta z, okay, fine. Okay, all right, then we can of course write down what is the rate of work done in the z direction again. So that would be minus partial y p times what? W, okay, yeah, this is z, good, times p times w, okay, plus partial x times tau x z multiplied with w plus partial y tau y z multiplied with w, partial z tau z multiplied with w. We have the elemental volume, that is delta x delta y delta z, okay. Okay, we have all these three. Now we can club all of them into a total rate of work done term, okay. So that would be what? W dot, right, the net rate of work done because of all the surface forces is what? So we have these three terms, partial x, partial y, partial z with pressure multiplied with u. Can we write using a nabla notation? If I were to write, that would be minus grad, right, with v multiplied with what? Dot what? P times u bar, right, that would give me all these three terms, okay. Again of course this is multiplied with the volume which I have not written, plus we have several terms here which of course I can repeat them here again. So that would be partial x u tau xx, partial y u tau yx, partial z tau z x times u, plus I am just writing down here again plus partial y v tau partial x v times tau xy V times tau yy, partial z, tau z times y times v, plus we have w tau xz, w tau yz, tau zz times w, okay. So, all these guys multiplied with delta x, delta y, delta z, right. Is that correct? Or any mistakes in the summing up? We can of course write this in a compact notation, right, using the index notation, right, in which we can club all these terms that we have, all these terms we have here, okay, because you have it on your notes. This was what? This was the w dot equals, okay, minus del dot p u bar, that is what we have, okay, plus we had these 9 terms, right. So, I can use index notation and then club them, all of them up into what? How do I write it? Partial xj, okay, times ui tau ij, right. Would that give me all the 9 terms? It will give me, right, it will give me all the 9 terms times delta x, delta y, delta z, right. So, this you have to verify because there is a double subscript, there is a repetition of the subscript that will add to summation, okay. So, essentially what you have to do is you have to substitute I equals 1, 2, 3 and j equals 1, 2, 3 at a time. So, essentially choose j equals 1 and plug in I equals 1, 2, 3, repeat and then plug in j equals 2 and then repeat again for all the i's and so on, and because there is a repeated index, they are all summed to, they will all sum up, okay. So, you can kind of write this in a index notation like this, okay. Very good. So, essentially we found the work done by the surface forces. Now, there is also amount of work done because of the gravity, right, essentially that one. So, that we will integrate using a source term, okay. So, let us call this source term as sum SE, okay. This is because of the work done on the fluid particle, let us say because of body forces, okay. That is what we have. Now, let us look at the net rate of heat transfer term, right. So, the net rate of heat transfer, right, to the fluid particle is what we want to look at now, okay. So, we will consider net rate of heat transfer because of conduction, okay. We are not considering the effects of radiation, okay. So, what do we have? We have, we will consider again the fluid element, which is x, y, z, and the heat flux vector that we have q bar is a basically qx I hat, qy j hat plus qz k hat, right. Essentially we have 3 components of the heat flux vector, okay. Again, if we define this q bar at the centroid, that is at x, y, z, we can reconstruct this on the faces, okay. On the faces, what would that be? That would be essentially the heat flux that is coming in, net heat flux rate would be qx minus partial qx by partial x delta x by 2, and the heat flux that is leaving through the face would be qx plus partial qx by partial x delta x by 2. Similarly, we have the heat flux coming in here, this is qy minus partial qy by partial y delta y by 2, and through here we have qy plus partial qy by partial y delta y by 2. Similarly, in the z direction, so this would be qz minus partial z qz delta z by 2, and whatever is leaving through the front face would be qz plus partial qz by partial z delta z by 2, okay. So, we have all these heat flux rates that are coming in and leaving, okay. So, the heat flux is coming through the west face and leaving through the east face, okay. So, we have to look at what is the net rate of heat transfer added to the fluid particle. So, q dot that is added would be what? Would be essentially whatever is being added from the west face would consider as positive, whatever is leaving from the east face would be negative. Okay. So, this would come out to be Qx minus partial Qx by partial x delta x by 2. Okay. I will first consider the x direction. Okay. So, this is being multiplied with delta y delta z would give me the heat transfer rate because this is the flux. Okay. So, I multiply with delta y delta z, this is being added, and then what is leaving the east face? This quantity is leaving the east face, right. So, this is minus q, this is minus qx plus partial qx by partial x delta x by 2 times delta y delta z, okay. That is being leaving. So, what terms will remain here? Again qx gets cancelled and then we have 2 halves of the partial derivative term here. So, they will add up to 1. So, that will be minus partial qx by partial x times delta x delta y delta z would be the term that retains in the heat transfer in the x direction, okay. Okay, that means what would be the total heat transfer that is being added to the fluid particle? This would be a summation of the x, y and z components, okay. That will be minus partial qx by partial x minus partial qy by partial y, partial qz by partial z times delta x delta y delta z. So, what is this? This is nothing but we have the q bar vector, right, and then we have nabla operator. How can I write this? This would be minus, is it a divergence or a gradient? It will be a divergence, right, it will be a divergence del dot q bar, right, times delta x delta y delta z, right. Okay. So, we can simply write like this, this is the total heat added. All right. Now, we are in a position to write down our total equation, okay, the energy equation, that is rho times d. Before we do that, I want to simplify this to let us say in terms of temperature. So, what does Fourier's law of heat conduction tell us? About heat flux vector and the temperature. What is Fourier's law of heat conduction for q bar? Q bar equals minus k grad T, right. There is a minus here, okay. Where does the minus come from? Because heat flows in the direction of decreasing temperature gradient, okay. Okay. So, essentially that is why you have a minus grad T. Now, we can plug back this into the above equation that we have. So, which gives us Q equals, so there is a minus here in this equation, okay, and there is a minus here. If I plug in substitute for Q bar as minus k grad T, we are going to get del dot k grad T, right. This is the heat added to the fluid particle, okay. All right. So, we are going to look at now the total essentially the energy equation, okay, that is given by rho times dE dt, okay, equals, what are the terms we have? We have the net rate of work done on the fluid particle, that is how much? That was minus del dot pu bar, okay, right, isn't it correct, okay, plus we have this 9 expressions, right, this gigantic expressions which we kind of wrote down in a compact form, okay. I will write it in a compact form here and then later on if we needed we will expand it. So, that was dou partial xj ui tau ij, right, is that correct? Yeah, would that give us all the 9 terms, okay, plus what else we have? K del dot k grad T coming from the heat, plus we have a source term for the gravity Se, okay. So, all these terms, this is our energy equation, all right. Now, what is this energy that we have for a fluid particle? What does it contain? E, the total energy that you have for a fluid particle is a summation of internal energy, right, which we usually represent in thermodynamics with U, but here we already have U as well as U bar, okay. So, we will represent with another letter E, okay. So, this is the little e is the internal energy for the fluid particle, plus you have kinetic energy, that is half of u square plus v square plus w square, right. Is this u v w same as the u v w we wrote before or different? It's the same, right, should be the same. Plus what else we have? We have the potential energy, okay. So we have the potential energy as well, so which is given by g times some elevation, okay. Now this potential energy that we have can be thought of in two different ways, okay. One is the way we write it here, in which the fluid particle or fluid element is storing potential energy. That is one way to look at it. The other way is to look at in terms of some work being done, okay, on the fluid particle by this gravitational field, okay. So essentially we have a gravitational field, okay, and this is doing work on the fluid particle, okay. So we would like to take this approach, in which case we don't have to write the potential energy term explicitly here, rather we can have a source term, okay, that takes care of doing work on the fluid particle, okay. As a result, we don't have this term here, but we would add a corresponding source term on the right hand side of the equation, okay, which is basically the gravitational field is doing work on the fluid particle, okay. Now essentially we end up with only then two terms, this E and half u square plus v square plus w square. Now we are doing all this because it is a common practice to write an energy equation for the internal energy E, okay, rather than the total energy capital E, okay. So essentially what we want to do is we initially want to have an equation for internal energy, and thereafter depending on the fluid we would like to have an equation for temperature, okay, if we have an incompressible fluid. So for that matter we are trying to derive what does E contain in terms of the little e and the kinetic energies, okay. Now what do we have to do? If we want to get an equation for little e, we have already an equation for capital E, we have to write an equation for the kinetic energies and subtract off that from the equation for capital E, right. Then we can get an equation for the little e that we have, okay. So that's what we're going to do. So now how do I get an equation for the kinetic energies? How do I get an equation for kinetic energy? Okay, essentially it is straightforward. You take the momentum equations, right? You already know the momentum equation. For example, if you take the x momentum equation, what we have is, what is the term on the left hand side? We have rho times du dt, right? So what I can do is I can multiply this with u. I can write it as rho times u times du dt, which is nothing but rho times half of du square by dt, right? So we got one term of this equation, right, like this. So essentially what we have to do is we have to multiply the x momentum equation with u, y momentum equation with v, and the z momentum equation with w, and then add all of them together. Then we are going to get an equation for d by dt of this quantity, that is half u square plus v square plus w square, right. Essentially what we have is we have an equation for, so our energy equation is rho times dE dt, right. This is nothing but rho times dE dt times E plus half u square plus v square plus w square. Now eventually we want to write an equation for rho dE dt, right. So we are trying to come up with an equation for this quantity, that is rho times d by dt of the kinetic energy, okay. So which we just found out that we can easily simply multiply the momentum equations on both sides with the corresponding velocity and then add them together, okay. So if I write the momentum equation, which you would help me write here. So what would be rho times du dt for the momentum equation? We had, you have to kind of flip your pages back and then tell me what is rho du dt. That is minus partial p partial x, right, plus partial x tau xx partial y tau yx plus partial z tau zx, right. plus we had some source term that we wrote it as Smx. Okay. So, this is our momentum equation in the x direction. Okay. So, we will multiply this with u, okay, that would give me rho u du dt, which is nothing but rho times half d by dt of u square equals minus u times partial p partial x plus u times partial x tau xx u times partial y tau yx plus u times partial z tau zx plus u times smx, right? Straightforward, we just multiplied that. Now, let us go back, okay, and try to write an equation also for v, okay, then we can kind of club it together. So, that will be rho half d by dt of v square would be how much? Minus v partial p partial y plus v times, anybody, partial x tau xy, v times partial y tau yy, v times partial z tau zy, right, plus v times smy. Okay. Okay, now we do not have to write the third expression, but what does these two equations have to do? We have to kind of club them together, right, to get half u square plus half v square. We have to sum these two equations together, plus we have to add the w equation as well. Okay, we add all of that, and then we realize that rho d by dt of with a half u square plus v square plus w square would be what? Would be a really long expression, right? What will be the first term of that? You have minus u partial p partial x, right, and you have minus v partial p partial y, and you have minus w partial p partial z. What is that? Can we write in a vector form? Minus u bar dot grad p, right, plus we have again these terms, that is u partial x, all these things, right. We have these 9 terms, right, 3 from each of these equations, which I am not repeating here. So, we have so many of these terms, plus what does the last term we have? U times smx plus v times smy, that is nothing but u bar dot sm bar, right. If I represent my source as a vector, then it will be u bar dot sm bar. Okay. Now, what we will do is we will kind of subtract it off in our mind and then try to write the total equation that we have here, okay, which I am going to take your help. So, essentially what will be the equation for then? Rho de dt minus half of rho d by dt of u square plus v square plus w square, that is nothing but your rho d little e dt, isn't it? Because this capital E contains this plus little e plus this half kinetic energy square. So, this is the equation we want to write. Now, you have to go back and see what are the terms that get retained here when we write to this equation. What is the pressure term in this case? The pressure term was del dot minus, was there a minus? Minus del dot p u bar. So, if I expand this, what will this be? This will be minus u bar dot grad p, right, minus p times del dot u bar, right. So, when I am subtracting this off, I have this term same as this term, right. So, what term would retain? Only this minus p times del dot u gets retained, okay. So, that means my equation for rho de dt would contain minus p times del dot u, right, because the equation for rho d capital E dt contains this term, which can be expanded into these two components, and one of the component already exists in the half kinetic energy equation, okay. Alright, so we have this first term. Now, what does the equation for rho de dt contain in terms of the tau xx, tau ij stress tensor and uvw? What we had was, we had a really long 9 terms just like here. Only thing was these terms, the u was inside the partial derivative, right. If you go back, what we had was we had partial x u tau xx, u tau yx and so on, right. So, if you expand that in a product rule, this is one of the terms, right. So, only the other term remains, is that correct? Yes, okay. So, only the other term remains, in which case what will be that term look like? That looks like the partial derivative should operate on the velocity instead of the shear stresses. That is the only term that retains. Okay. Then we can write it as plus. Okay. Can you help me write this? What term gets retained? So, if I write it here, your E derivative equation contained partial x u tau xx, right? Whereas your KE equation contains term like u tau xx by dou x, right. So, in the equation for little e, we will have only a term that is tau xx times partial u partial x, right. So, and so on, okay. So, this will be tau xx partial u partial x plus tau y x partial u partial y tau z x partial u partial z, okay, plus we will have what? We will have tau x y partial v partial x, tau y y partial v partial y plus tau z y partial v partial z plus tau x z partial w partial x plus tau y z partial w partial y plus tau z z partial w partial z. Is that correct? Any mistakes? So, the second index should be y and x, y, z, and the first equation should go as the first terms. That should be compatible with the denominator of the partial derivative, right? Fine. This is perfect. This is correct. Okay. So, we now just have simplified these equations, plus what is the remaining terms we have coming from the capital E equation? Source term. So, that is essentially we have this del dot k grad t as well, right. So, that was del dot k grad t plus coming to the source term, what was the source term we had for the capital E equation? We wrote something like SE to account for all the gravity and all the body forces, and in the equation for kinetic energy we had u bar dot Sm bar, right. Remember here? Okay. So, now I define another new source term. That source term for little e would be, I would call it S little e, which is nothing but S capital E minus u bar dot Sm bar, okay. I would just simply write it as S little e. Of course, this also can be simplified, minus p del dot u plus I can write this as tau I j what partial u j partial x I plus del dot k grad t plus S little e, okay. That is a very simple equation, okay. Okay, now we got an equation for internal energy. Let us take a particular case of an incompressible fluid or an incompressible flow, in which case your internal energy E for a fluid, okay, which is incompressible. What is little e? The E is nothing but your internal energy. Internal energy can be expressed in terms of specific heat and temperature. For a fluid, you have only one specific heat, right? It's just C. We'll call it C times T, okay, where C is the specific heat and T is your temperature, okay. What about for an incompressible fluid? This quantity del dot U bar? 0, right? This is 0 for an incompressible fluid, which we have established in the context of mass conservation, okay. So, that means if we go to this equation, we can plug in E equals Ct in this equation, and this term goes to 0. So, the only things we are left with is these 9 gigantic terms and then the heat conduction and so on, okay. So, we can now write down an equation for temperature, that is the energy equation for an incompressible fluid, that is rho times C times d capital T by d little t, okay, equals this expression tau ij partial uj by partial xi plus del dot k grad t plus s little e. Okay. So, that is your energy equation, for an incompressible fluid. Okay. Of course, we have not yet closed how to calculate these shear stresses, right. We do not have a model about these shear stresses, that we will do, and that is what defines a fluid, okay, to be either Newtonian or non-Newtonian, that we have to see. Questions till now? So, you would essentially solve this energy equation in terms of temperature for an incompressible fluid. Okay. Okay, so this is nice and good, but for compressible flows, you would usually work with enthalpy. Okay, if you are dealing with compressible flows, which we are actually not discussing the solution algorithms here as part of this course, but for the sake of completeness, I would write it down here. So, if we have compressible flow, you would get an equation, you will write equations in terms of enthalpy, because that is much more easier to work with. Okay. So, enthalpy would be summation of what? Your internal energy and the flow work, right, the product of the pressure times the what? Specific volume. So, this is little v. Okay. We will work with this equation. So, this is nothing but what? So, I can write this as E plus, so this is nothing but E plus P upon rho, okay, 1 upon density is your specific volume. So, your E is what? So, if I write your, so I can write H equals E plus, so my E is Cp, okay. So, I can also calculate what is my total enthalpy, right, or stagnation enthalpy, okay. That would be what? That would be H naught equals H plus the kinetic energy, right, essentially plus half U square plus V square plus W square, okay. So, that means I can plug in H equals E plus P upon rho plus half U square plus V square plus W square. Now, we can rewrite this expression as H naught equals what is little e plus half U square plus V square plus W square. That is my capital E, right, without the gravity terms in there. So, this is capital E plus P upon rho, okay. Now, what I can do is for compressible flow, I would write an equation for H naught, okay, the total enthalpy, okay, that would be rho times d H naught by dt, which is also the same as partial T rho H naught plus del dot rho H naught times U bar, right, we just introduced the transformation, equals something on the right hand side, right. Now, how do we get this something on the right hand side? You plug in what is H naught, H naught is your E plus P by rho, plug in E plus P by rho into this equation, right, which will give you dE by dt plus d by dt of P, right, with a minus, okay, plug into that. So, essentially get an equation for dE dt, okay, get an equation for dE dt, substitute that back into this equation, okay, for dE dt. So, you will only get an extra term, that is dP dt, right, that is what you will get. And do you have an equation for dE dt or rho dE dt in that sense? We have already derived an equation for rho dE dt, okay. So, substitute that, then you would get an equation for this enthalpy, and then you can finish an equation for total stagnation enthalpy here in terms of the tau ij, U and pressure and so on, okay, that you can easily obtain by substituting for rho dE dt from the previous equation we have already derived, okay.